So hope you have done this in our last class. Tell me whether you have done it or not. Right? Okay, let's go to the next one. Have you done this? This is done? Okay? Very good. Now you see this. See here, in this example, what you have got is sum of products, right? Quite straightforward. Many of you have practiced it. If the question is given like this, right? So you just have to simplify the Boolean expression given in a canonical form. This is called as canonical form. Okay? Instead of writing very big equation, you're going to write your Boolean equation like this. Hope all of you understood what is the purpose of having canonical form. Is it practical to write A bar, B bar, C bar, D bar plus A bar, B bar, C bar, D plus, is it practical to write such a big equation? That is the purpose we write this canonical form. This is called canonical form of representing Boolean equation. As usual, yesterday I taught you, most of you have done practice also, how to solve this using Karnaugh map for sum of products. Remember, sum of products. Now you all know that there is one more form of representing Boolean equation. What is that? Product of sum. Right. For that, I have told you in my beginning of Karnaugh map lecture that you consider zeros. Can you see here? For sum of products, when you put all ones, min terms, remaining places it is supposed to be 0. It is 0. That means you put 0 here, 0 here, 0 here. Okay? And then 0 here, 0 here, 0 here, 0. Wherever you don't have 1, in that place you try to put 0. Right? So I am just putting 0, 0, 0 here, 0 here, there is no 1 here, 0, 0, 0, 0. Right? First you do that. You know why we are doing this? To get the product of sum form. Listen carefully. Okay, so we get something like this. Right? We get something like this. Try to group it. Try to group it. Now, are you going to group ones? No. You are going to group zeros. Right? Grouping system is same. Grouping method is same. Try to group maximum number of zeros as possible, if it is possible, and try to get the expression. Okay. Now, in this case, you can see that this can be grouped. Yes or no? This can be grouped, and also this can be grouped. This can be grouped. Now, what is remaining now? Now, see, now some people may say, can I group this? Why do you need to group when this is possible for you, right? Why do you need to group this when you can group this, this, and this? Right? Okay. Now, getting the literal, see, first you write in the form of sum of products. Whatever result you get, listen carefully. Whatever result you get, first you write in the sum of products. After that, you can take complement from both the side and you can simplify it to bring it to the normal form. Okay. Now you get the actual sum of products expression for this combination of zeros. Can you tell me what is the expression corresponding to this combination, this group? CD. So this is CD, let's come here. what is the expression for this? Expression for this is going to be AB, that is this one. Similarly, expression for this, what is the expression for this? Right? So what is common between these two? B, right? B, what is common between this and this? D bar. It is BD bar. So this is going to be BD bar. Now, see here, this is still in the sum of products form, right? Still in the sum of products form. So what you do is, now you take the complement of that. Right? You take the complement of that. So now, what exactly is this? See, this is now your F is equal to, see, so what you get here is F complement. Why it is F complement? Because you are combining zeros. If you combine ones, you will get F. Remember that. Now, what you get after combining 0 is F complement. So what you get is F complement. Okay. Now, how do you get F from there? If you want to get F, take complement once again. Now, see here, when you take complement once again, okay, when you take complement once again, see here, you get AB plus CD plus BD bar whole bar. Right. So now, can you write it's using De Morgan's theorem? Can you simplify it now? Come on, how do you simplify it using De Morgan's theorem? Exactly, it is AB bar into CD bar into BD bar. Now can you tell me once again, can you apply De Morgan's theorem for this? AB whole bar is equal to A bar plus B bar into, what is C bar D? C bar plus D. Sorry, C bar into D bar. C bar plus D bar, exactly. Into, can you tell me? So this is BD bar, okay? BD bar. This is now B bar plus D. B plus D. Because you will get have you understood this? Simplification using, how did you simplify this? Using De Morgan's theorem. Using De Morgan's theorem, we have simplified this. Now, can you tell me what is this form now? Product of sum. Okay? Product of sum. This is the POS, product of sum. Okay? Have you understood this? The previous one is, ultimately you are going to get F only, right? This is F only, right? See, this is F, F bar is. So whenever it has been asked to write the result using product of sum, instead of combining 0, what you should combine? Instead of combining 1, what you should combine? Zeros. Right? After that, write the expression in SOP only. But that is not F. That is going to be your F bar. What you get is F bar here. Now, how do you get your F? Take one more complement and simplify it using De Morgan's theorem. That's all. You will get your actual F in the form of product of sum. Product of sum. Let's do more examples. You can learn better about this. Now, next, there is one more very important concept. We call it as don't cares. What is this don't care? Whatever you do, either you go there or don't go, doesn't matter for me, I don't care. What is that? Normally we say, right? Don't cares. See, this variable, normally when we write in the equation, right, it can be either, we say it is either 0 or 1, right. See here, now if you write the truth table, okay, for 4 variable, okay, if you write 0 0 0 0, okay, write all combinations. Okay, see, how do you convert this into truth table? How do you convert this truth table? See, you have A, B, C, D, right? So how many combinations possible? 0 0 0 0, right? 0 0 0 1, 0 0 1 0, 0 0 1 1, right? 0 1 0 0, 0 1 0 1, 0 1 1 0, 0 1 1 1, right? After that 1 0 0 0, 1 0 0 1, okay, and then 1 0 1 0, then 1 0 1 1, 1 1 0 0, 1 1 1 0, 1 1 1 1, yes or no? 1 1 0 1, yes, whatever it be, okay, you write the proper, okay. So now see here you have 1, that means if you take the output F here, okay, for 1, that is, this is the minterm corresponding to M1, right? That means this is 1, output is 1, okay. That's what actually this equation represents, right? Now similarly, where and all you have 1, 3, 3 7 11, 3 7, where is 7, 7, and then 3 7 11 and 15, right? Somewhere 15 is here, I'll just write, see, 1 output 1 here. All remaining places it is 0. This is what this equation represents. Suppose if don't cares are not defined, right? It says that all these output F, for all these combinations, output F is 1. For remaining it is 0. That's what this equation represents. You can check it using truth table. Now, what is a don't care? See, in this truth table, I have defined that your 0, okay, and 2 and 4, 5, all these are, I have defined it to be 0. I defined it to be 0, right? And all remaining combination, it has been defined as 1. Suppose, if I say 0, 2, 5 are don't cares. If I say 0, 2, 5 are don't cares. If I say this 0, okay, 2, and 5 are don't cares, means this F for that combination of inputs, F is either 0 or 1. That's called don't cares. We are assuming it. It's just an assumption, okay, for simplification. Assume that this 2 combinations are don't care. What is the meaning of that actually? What is the meaning of that? Why I say that whenever input to this logic function is 0, 0, 0, 0, my output F, it's don't care, right? And similarly, when the input is say 0, 0, 1, 0, this is don't care. It is represented by X normally. This means that this input is not, it's a dummy input. I'm not bothered about what's going to happen whenever this input combination is coming to the logic circuit. I say dummy, it's dummy, right? When that input combination which I'm going to consider is dummy for me, do I bother about the output? I don't consider that input at all, right? Right, so for this logic circuit, okay, of course, when the inputs are 1, now what's that, 1, 3, of course, output will be 1 only, I am bothered about it, okay. Now, if I say that 0, 5 are don't cares, that means instead of 0, I am going to put x here. That means it is either 1 or 0, either 1 or 0, right? That's why we call that as a don't care condition. And when the don't care condition comes, that for this particular input, I am not bothered about my output at all. Have you understood this? Now, where it is useful? Right, this is useful when you just try to simplify your Karnaugh map, right? So now, when, as usual, okay, in the Karnaugh map, when you put this in the Karnaugh map, for all this combination you put ones, right? Everywhere, whichever minterms are here, you are going to put 1 there. Now, in this place, what you put, tell me? Instead of putting 0 or 1, you put x, 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 x. That's all. Only the change is that whenever don't care is defined in the question, take it as x, x, x. Now see here, which are all now x, x here? 0 is x. See, here you have a x. Here you have a x. Okay? And now, there is one more, right? There is one more x here. Now, once again I am telling you that while simplifying Karnaugh map, getting a group of all ones is compulsory. Okay. Now, while grouping, if there is an x there and using that x, you can get advantage of getting group of 8 or group of 4, use that x. Have you understood this? Use that x. Right. For example, see here you have x, here you have 1, here you have 1, here you have x. Now, you have the option, right, to combine including x here. You have the option to combine including x. You can just group this. This x can be used in grouping whenever you have the option to group it. See here. Right? If don't care is not defined, can you do this? If don't care is not defined, you cannot do this, right? Okay? So, include x in your grouping. In that process, if you are not able to include one x at all in any group, doesn't matter, don't worry about it. In this example, see, while combining this, these two ones are included in the group, and you have included these two x also because it is a don't care. What is the expression you get for this, tell me? What is the expression you get for this? Combination of this. A bar, B bar, right? See, look at this. All this will get cancelled. So, you get A bar, B bar plus, okay, what is another combination possible? So, another grouping possible is this one. What is the expression for this? CD, that is CD. Now, can you check all ones are covered? All ones are grouped? Done. Don't worry that there is one x left here. Not required, it's a dummy, it's don't care. You need not put circle and include it with anything. You need not do this once again, not required. Not required. Have you understood this now? Okay, so have you understood about don't cares? And in the examination, in the question, it will be given to you that what are don't cares. Now, have you understood the concept of don't care? Right? That means in that truth table, in that logic circuit, whatever combinations are mentioned as a don't care is not a botheration at all. It's dummy inputs. It's not defined. It's as if not designed. Whether defined, whether output is going to be 0 or 1, you're not bothered about it. Have you understood? That's called as don't cares. So, have you understood about don't care now? Right? And while grouping, I said it can be either 0 or 1. Okay? You can consider this as 1 and group it. That's why we group using this don't care also. If there is no don't care, don't do that. If x is not given, you cannot do this. You can do only this in this example. Have you understood this? Okay, keep it in mind. Solve some more problems. I am just sending you a lot of problems to solve. Either it is solved or unsolved. Do that one by one. Yesterday I sent one problem, right? I don't know, some of you have done it. I told you that you just text me, right? whatever you have done, it's very easy, right? People have not done, only few have done it, okay? But try to have a good spirit of, need not be. Still here, for example, listen carefully. Now, here I have 1, assume here I have 1, right? Here you have 1, here you have 1, here x. This also can be combined, need not be, yes, no? Including don't cares and ones, it should be either 2, 4, 8 or 16 like that. I have understood. That grouping is only possible. See, we are presuming that this x to be 1, right? We are presuming x to be 1 and we are combining it. Because don't care means it is either 1 or 0, right? Okay. So this completes a 4 variable Karnaugh map, okay? See, this is also possible, yes or no? Is there any other combination possible? See here, either you use this or you use this. Have understood this? This is also possible, right? This is also possible, this is also possible. See, you have 2 possibility, either this one and this one, okay, or this one or this one. Any one you can use, right? So when you do that, what you will get is a bar d plus cd. Expression will be different, doesn't matter, no, don't worry, it is simplified form once again, fine. So let's see, try to do all these things, okay? See, reduce this, right? It's simple your algebraic simplification, right? So multiply b, see, okay? So you can take b outside from here, right? When you take b outside from here, you will have 1 plus c. What is 1 plus c? It is b only, right? Okay. So then similarly b plus b bar c. Simplify this. You can use simple boolean laws and you can simplify this, okay? Simplify this. Just try to practice this. I'm not going to do this. I will directly go to the combinational circuit from here, okay? You can multiply. See, this is going to be 1, then you have b plus b bar c, b bar, just try to multiply this, b into b into b bar. What is b into b bar? B, right? Okay. B into b bar is not 0. B into b, exactly, yes, b into b bar, exactly, yes. Try to, these things, certain things will get cancelled, okay? And you can just go ahead with the final answer, okay? This is easy. Just you need to practice, that's all. Okay? Boolean laws, you're supposed to remember. Boolean laws are very simple, these things. Understood this, okay? Now, next we will go for one more topic called as combinational circuits. What is this combinational circuits? Okay. So at this point, what are the concepts you know in digital design? You know about, we all started from a logic elements and or and gate. We started with that, right? And we have written logic equation, logic functions, we call it the boolean functions. And we also have seen how to simplify a big boolean function into a simpler function, right? We have done that, right? We also know how to write an equation when the truth table is given, right? When the truth table is given, that is the behavior of the circuit. You can write the boolean equation for that, yes or no? Right? How to write that? How do you convert from truth table to Karnaugh map and Karnaugh map to boolean function? It's very easy, right? See, I have told you just now that In truth table, you will be having something like this. Suppose if you have 3 variable, 3 inputs to your digital logic, what you call as logic circuits. Suppose you have a circuit, you have a digital circuit, and digital circuit has 3 inputs, 1 output. Assume that you have 3 inputs and 1 output, and you know the behavior of that. That's the truth table. Yes or no? Right? See, I have a digital circuit like this. This is my, I'm just writing as a black box here. This is my input, and this is going to be the output. And this is your digital circuit, or call it as a logic circuit, whatever it is. Logic circuit. Truth table is nothing but the behavior of this. Suppose if I take this, I want to see what is my output F for various combinations of ABC. So your ABC is a boolean variable, right? It can take either 0 or 1 only. It cannot take anything else. That means for 3 input variable, how many variations of inputs possible? 8. 8 variations, right? So my ABC can be 0, 0, 0. My ABC can be 0, 0, 1. My ABC can be 0, 1, 0. It can be 0, 1, 1. It can be 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1. These are the combinations, right? And my truth table will tell me what is my output. What is my output? Have you understood this? Your truth table will tell what is the output. Now suppose if I say, if I take it as a full adder, I told you about full adder, right? What is full adder? It's nothing but an adder with carry in, right? Have you understood this? Okay, now can you tell me suppose if this is a full adder, can you tell me what is the sum? For this it is 0, it is 1, for here 1, here, what is the sum here? What is the sum? Is it 1? Sum is 0, I am asking only, okay, carry will be there, don't worry, right? It is 0, yes or no? Okay, for this 1, for this, and for this, 1, carry will be 1. Understood this? Okay, now you know that if it is a half full adder, suppose this is yes, this is going to be your sum output. So how do you get a Boolean equation for sum now? Use Karnaugh map now. Have you understood this? Use Karnaugh map. Right. So how do you use Karnaugh map now? To simplify, to get an expression for this. This is A, this is BC, yes or no? Now, what are the minterms in this? See, all these are called minterms. Wherever 1 is there, it's called minterms. Okay? Once again, you know this is 0, 1, 2, 3, 4, 5, 6, 7. See, I think this is 1, right? 1 plus 1, 0, with the carry 1, right? And that carry 1 plus 0, output is going to be 1, right? Okay, anyway, we'll check it, no problem, don't worry, okay? We'll see we'll get the expression. Expression, we should get it as A XOR B XOR C. If you don't get that, then this is wrong, okay? Now, okay, where and all you should put 1? You should put 1 here. Okay, I'll use a different color, don't worry. You should put it as You should put 1 here, then there is 1 in 2, and then there is 1 in 1 0 0 4, and that's 7. Yes, correct. Understood this? Okay, now how do you simplify this? Is there any combinations possible for you? Where you will do? Come on. In such cases, what you will do? No combinations possible, right? Write the equation as it is, just combine this. Can you tell me what is your yes is? This is your A bar, this is B bar, C bar, this is B, C bar, BC, B bar, C bar. Sorry, it is B. Yeah, of course, I'll just do the changes. This is A bar, A, B bar, C bar, B, C bar. This should be B bar, C, 0, 1, right? 0, 1. Exactly. This should be B bar, C, BC. This is BC bar. Now, can you tell me what is the expression for sum? See, what is the expression for this? What is the expression for this? Come on, tell me. A bar, B bar, C plus. What is the expression for this? A bar, B, C bar plus. What is the expression for this? A, B bar, C bar plus. This is A into B into C. Okay, is there any simplification possible here? See here, listen carefully. Now, you check any simplification is possible. Can you write it in terms of XOR gate? Right? Okay, see here. I will take A bar outside from here, right? Okay? I will take A bar outside. Right? Now, inside this, you have B bar C plus BC bar, right? Yes or no? Is it okay? Now, and what I will do here is, I will take A outside here. Right? I will take A outside here. You will have B bar, C bar plus BC. Is it okay? Have you understood this now? See, I will bring it in the form of a XOR operation. See here. Right? Your sum is equal to, I will bring it to the form of A XOR B XOR C. See how it is possible. Listen carefully. Now tell me, what is this actually? That is B XOR C, right? Yes or no? Now what is this, tell me? B XOR C whole bar, right? Yes or no? What is this? B bar C bar plus BC. It is B XOR C whole bar. I have understood this. This is nothing but, see, I will rewrite once again this one in the next page. Right? See, I'm just going to continue this to the next page. Listen carefully. See, you will have A bar, okay? And what is this inside? I said B XOR C. Plus you have A here, right? And what is there inside? B bar C bar plus BC. This is nothing but B XOR C whole bar. You can prove it. You can prove it using truth table, right? Have understood this? So do one thing. You just B bar C bar plus BC. Okay, take a complement and use De Morgan's theorem here. Take a complement. Use De Morgan's theorem. See what you will get. Right? Definitely you will get B XOR C whole bar. Right? You solve this. Okay. Exactly. Now you see here, listen carefully, you have A bar into B XOR C plus, see here, you have A into B XOR C whole bar. Can you tell me what is this now? It is A XOR B XOR C. A XOR B XOR C. Is it not? We got the expression, final expression. So your sum is equal to A XOR B XOR C. Now can you implement it using gates? Yes or no? You can implement it using XOR gate. XOR gate is available, right? Right? You know what's the symbol of XOR gate, and you know how to do that. Now I will write how many XOR gates are required now for my sum. One XOR gate, another XOR gate. You are almost done with the next chapter, which I am going to teach you. This is what actually next chapter is. This is A, this is B, okay, and then XOR of, okay, it's left to you how you use the variable, right? So it is A XOR B XOR C. You can use it like this, right? When the expression is A XOR B XOR C, you can use, either you can use BC here or anything you can use, okay? Then this is going to be C. And what are you going to get here is sum. And what is this? What you have done? Tell me. Implementing the full adder. Implementation of full adder. Right. This is nothing but your full adder. Now, this is your full adder. From where you started your design? Tell me, from where you started your design? You have started all the way from your truth table. You started from here. This is the behavior of the circuit which is required. I had just drawn it as a black box here. I said there is a digital circuit and 3 inputs and 1 output. And I told you that this truth table is the behavior of that. And I am asking you to get the logic circuit. So what you did? You have the truth table, converted your truth table into, what is this? KMAP. From KMAP you got the equation. You have simplified the equation. It is found to be A XOR B XOR C, and you have implemented it using XOR gate. That's all. This is called as combinational circuit. This is called as combinational circuit. And this is a circuit for full adder. That's all. Your combinational circuits are nothing but this. You will have many requirements for your digital domain. Right? You're talking about digital domain, digital economy, digital. Everybody is talking digital. What is this? This is what actually. This is for full adder. Similarly, you have a lot of other logic functions required for your everyday digital operations, and you're going to design it. That's what your digital design is. right? Have you understood what this is? A combinational circuit, and this combinational circuit is for full adder. Similarly, you have full subtractor, you have half adder, you have encoder, decoder, multiplexer. Okay, lot of digital, what you call it as combinational components are there. That's what you're going to study, right? Have you understood this? Fine. Okay. So I was trying to introduce you about a combinational circuit. Hope now you all understood what is combinational circuit. This is what combinational circuit is. In this combination circuit, one thing you observe, your output depend on present input only. Have you understood? Here, if your sum, whatever sum you are getting, it only depends on the input at that time only. It doesn't depend on input from the previous time. Have you understood this? Okay? Hence, this output depends on only inputs at the present time. It is called as combination circuit. If at all, if your output depends on a previous time instant, such circuits are called as sequential circuits. Sequential circuits. There you require something called memory element to keep the previous bit, right? So in this case, in combinational case, you have only the present input. Your present output depends on only the present inputs. It doesn't depend on any previous output, not previous input, previous output. If at all it is depending on a previous output, such circuits are called as sequential. We will come back to that, don't worry, okay. So hope all of you understood at this point, okay, what is a combinational circuit. You have a half adder, full adder, you already done. Can you do it for half adder for me? Do it yourself. I have done half adder, right? Full adder, right? Can you do it full adder? Arey yaar, only the truth table is different, right? Input is only 2. Can't you do it? In 2 minutes you can do. Can you do it? In 2 minutes you can do. 2 minutes, enough for you. When you've done it for full adder, write the truth table. Truth table for half adder. Okay? Okay, next class, please, all of you come with the proper internet in your system, in your mobile phone. Right? Okay?